Welcome back to Cosmos in a Pod. This is our Space and Astronomy series, episode 11. And today we're going to be doing a deep dive into the fascinating process of starbirth.
Yeah,
How stars, these engines of the universe, come into existence.
I'm really excited about this one.
Me too.
Yeah.
And you know what's really cool about understanding starbirth? It's not just about stars themselves. It unlocks secrets about the elements that form everything around us.
Right, exactly.
Even planets and life itself.
Yeah, that's what's so fascinating. We're not just talking about twinkling lights in the sky, right?
Yeah.
Stars are the fundamental building blocks of the universe.
Yeah.
They create the elements that make up everything around us.
Literally everything.
You made this podcasting equipment.
Wow.
It all started with a star.
I mean, that is a pretty incredible thought, isn't it?
It is.
To think that we're all made of stardust.
Yeah.
But where did these stellar giants even come from?
Yeah, they don't just magically appear, do they? It all begins in these vast clouds of gas and dust called nebulae. Yeah, think of them as cosmic nurseries filled with the raw materials for star formation.
So nebulae are like the cosmic kitchens where stars are cooked up.
I like that analogy.
What are they even made of?
So, primarily hydrogen, which is the most abundant element in the universe.
Right.
With a little sprinkle of helium and some traces of heavier elements.
Okay.
Now, these nebulae can span light years across, and they're not just massive, they're also visually stunning. Through telescopes, they look like celestial tapestries glowing with vibrant colors.
I'm picturing like these massive clouds of gas and dust just floating around in space. It's hard to even grasp the scale of it all.
It's mind-boggling.
It really is. But how do these clouds go from being just diffuse gas to becoming stars?
Well, that's where gravity steps. And gravity is like the master sculptor of the universe.
Right.
It pulls things together, and in the case of nebulae, it can trigger the collapse of these clouds, leading to the birth of stars.
So gravity is like the cosmic matchmaker.
Yeah.
Bringing all this gas and dust together.
It's neat all together.
But what sets off this chain reaction?
Right. What causes these clouds to start collapsing in the first place? Well, think of it like a cosmic domino effect. Something needs to nudge those dominoes right.
Yeah.
It could be a shockwave from a nearby supernova, the death of a massive star, or it could be the collision of two galaxies, sending ripples through space that disturb these clouds.
So it's like a cosmic chain reaction.
Exactly.
With one event triggering the next, leading to the birth of new stars.
That's the beauty of it.
That's amazing. But let's focus on that collapse for a moment. What happens inside these clouds when gravity takes over?
So as gravity pulls the gas and dust inward, it forms these dense clumps called cores.
Cores.
Yeah, imagine a snowball gathering more and more snow as it rolls downhill.
Okay.
These cores are like stellar embryos, the seeds of future stars.
Okay, so we have these dense clumps of gas and dust, these cores.
Right.
What happens to them as they continue to collapse under their own gravity?
As they contract, they heat up and start to spin. It's like a figure skater pulling their arms and spinning faster and faster.
Oh.
And this spinning motion flattens the collapsing material into a disk, with most of the mass concentrated at the center.
So it's like a cosmic ballet.
It is.
With gravity and rotation shaping these stellar embryos.
Yeah.
And what's at the center of this disk? Is that the star?
Almost. That central mass is what we call a protostar. It's a young forming star that hasn't quite ignited yet.
Hold on. You're saying a protostar isn't a real star? What's missing? What makes a star a star?
The key ingredient is nuclear fusion. That's the process where hydrogen atoms fuse together to form helium, releasing a tremendous amount of energy. That energy is what makes stars shine.
Okay, so a protostar is like a star in waiting.
Exactly.
Still gathering material and getting ready for that big fusion moment.
It's building up to the main event.
But if they haven't ignited yet, how do we even know they exist?
That's a great question. Even though they're shrouded in cocoons of gas and dust, protostars aren't completely invisible. They emit infrared radiation, which we can detect with telescopes.
Gotcha.
It's like seeing a faint heat signature, a telltale sign that a star is being born.
So we're literally peering into stellar nurseries
We are.
and witnessing the birth of stars.
It's incredible, isn't it?
That is really cool. But you mentioned that these protostars are still gathering material.
Yeah.
Where's this material coming from?
It's all around them. Remember that spinning disk we talked about?
Yeah.
It's filled with gas and dust that continues to fall onto the protostar like rain feeding a growing river.
So it's a constant process of accretion, with the protostar gobbling up more and more material from its surroundings. But is this a peaceful process, or are there some dramatic events happening as well?
Well, it's not exactly a quiet tea party. As the protostar grows, it throws some pretty impressive tantrums. Powerful jets of gas called bipolar outflows shoot out from its poles.
Bipolar outflows. That sounds intense. What causes these jets and what do they do?
Think of it like the protostar clearing its throat, getting rid of excess material as it feeds. These jets can extend for light years, blasting away gas and dust carving cavities in the surrounding nebula.
It's like the protostar is saying, make way, folks. A star is being born here.
Exactly. It needs its space.
But how do these bipolar outflows actually form? It sounds like there are some pretty intense forces at work.
Absolutely. It has to do with the interplay between gravity, rotation, and magnetic fields.
Oh, wow.
It's a bit complex, but essentially the spinning motion and magnetic fields of the protostar channel material outwards, creating these powerful jets.
So we have this protostar growing larger by the minute, blasting away material with these intense jets. What happens next? When does a protostar finally become a real star?
That happens when the core of the protostar reaches a critical temperature about 10 million degrees Celsius.
Okay.
That's when the nuclear fusion engine ignites.
Whoa. It's like flipping a switch and suddenly, boom, a star is born. What happens at that moment of ignition?
It's not just a moment, it's a process. As the core temperature and pressure increase, hydrogen atoms are forced closer and closer together until they finally overcome their natural repulsion and fuse to form helium.
So it's like a cosmic pressure cooker,
It is.
squeezing those hydrogen atoms until they fuse.
Exactly.
And what happens to the energy released by this fusion process?
That energy is what makes the star shine. It creates outward pressure that counteracts the inward pull of gravity. It's like a cosmic balancing act. Gravity pulling in fusion, pushing out, and the star finding its perfect equilibrium.
So a star is born from this delicate balance between gravity and nuclear fusion.
That's the essence of it.
That's amazing. But what determines what kind of star will form? Are all stars created equal?
Not at all. The mass of the protostar plays a crucial role in determining the fate of the star. More massive protostars will form larger, hotter, and more luminous stars,
Okay.
while smaller protostars will give rise to cooler, dimmer, and longer-lived stars.
So it's like a cosmic recipe,
It is.
with mass being the key ingredient that determines the outcome.
The mass is everything.
But what if a protostar doesn't have enough mass to ignite nuclear fusion? What happens then?
That's where things get a bit more unconventional. If a protostar doesn't reach a critical mass, it never quite makes it to stardom. It becomes what we call a brown dwarf.
Brown dwarf. So it's like the almost stars. Like they tried out for the cosmic choir but didn't quite hit the high notes.
That's a great analogy. Brown dwarfs are these fascinating objects that straddle the line between stars and planets. They're bigger than planets, but not quite massive enough to sustain nuclear fusion like a star.
So they're kind of like the cosmic underachievers.
You could say that.
But even if they don't shine as brightly as stars, they must still be pretty interesting to study.
Absolutely. Brown dwarfs offer unique insights into the lower limits of star formation and the diversity of objects that populate the universe.
So we've seen how gravity kickstarts this whole process.
Yeah.
But what happens next inside these collapsing clouds? That's where things get really interesting.
It sure does. Yeah, it's like a cosmic ecosystem, isn't it? The birth of a star doesn't just happen in isolation. It transforms the entire surrounding nebula.
Yeah, you're right. It's like a ripple effect spreading outwards from that newborn star.
Exactly.
So how does the birth of a star impact the nebula it's born from?
So the intense radiation and powerful stellar winds from these newborn stars, they kind of blow away the remaining gas and dust, carving out vast cavities and sculpting the nebula into these intricate shapes.
So it's like the star is flexing its muscles, pushing away the remnants of its birth cloud?
Yeah, you could say that.
Are there any famous examples of these sculpted nebulae that we can actually see?
Oh, absolutely. One of the most iconic examples are the pillars of creation in the Eagle Nebula.
Oh, yeah.
These towering columns of gas and dust, they're literally where stars are being born, illuminated by the intense radiation of nearby young stars.
Wow, the pillars of creation. I've seen pictures of those. They're absolutely breathtaking.
They are incredible.
It's amazing to think that those structures are being shaped by the very stars they're giving birth to.
Yeah, it's a beautiful illustration of the dynamic interplay between stars and their environment. And this sculpting process can actually trigger a chain reaction leading to the birth of even more stars.
Oh, wow. So it's a self-propagating cycle.
It is.
One star's birth can trigger the formation of many others.
Exactly. The shockwaves from stellar winds and supernovae can compress nearby gas and dust, creating new stellar nurseries and perpetuating the cycle of star birth. It's a cosmic dance of creation and destruction.
That's incredible. It makes you realize that the universe is constantly evolving, with new stars being born all the time. But what about the stars themselves? Once a star ignites and reaches that stable state,
Right.
what happens next?
Well, that stable state, what we call the main sequence, can last for millions, billions, or even trillions of years, depending on the star's mass.
Wait, trillions of years?
Hmm.
That's an incredibly long time.
It is.
What's happening inside a star during this main sequence phase?
It's all about balance. The outward pressure from nuclear fusion in the core perfectly counteracts the inward pull of gravity. It's this delicate equilibrium that allows the star to shine steadily for eons.
So it's like a cosmic tug of war with gravity and fusion locked in this epic battle.
Yeah, that's a great way to put it. And during this epic battle, the star is converting hydrogen to helium in its core, producing the energy that makes it shine.
Okay, but what happens when the star starts to run out of hydrogen fuel? Does the party just end?
Not quite. The star has a few tricks up its sleeve. As the hydrogen in the core depletes, the core starts to contract.
Okay.
And this causes the temperature and pressure to rise even further.
So like the star is trying to squeeze every last bit of energy out of its remaining fuel.
Exactly. It's trying to keep the party going.
But what happens when even that fuel runs out?
That's when things get really interesting. For stars like our sun, the next stage involves fusing helium into carbon and oxygen. This process releases even more energy, causing the star's outer layers to expand and cool, transforming it into a red giant.
A red giant.
Yes.
Those are the enormous reddish stars we see in the night sky, right?
Exactly. And while this expansion might seem impressive, it's actually a sign that the star is approaching its twilight years.
So even giants have their limits.
They do.
But what happens after a star has burned through all its helium? What's the final curtain call for a red giant?
Well, that depends on the star's mass.
Okay.
For smaller stars, like our sun, the outer layers will eventually drift off into space, forming a beautiful planetary nebula, leaving behind a dense, hot core called a white dwarf.
Wait, so the death of a star can be beautiful?
It can be a stunning sight.
I always imagined it would be more of an explosive event.
Well, it can be both. While smaller stars fade away gracefully, massive stars go out with a supernova.
Now we're talking.
Yes.
Supernovae.
Yes.
Those are the cosmic fireworks shows I've heard about.
Exactly.
Tell me more about those.
So when a massive star exhausts its nuclear fuel, its core collapses catastrophically.
Oh, wow.
This collapse triggers a shockwave that rips through the star, causing it to explode with unimaginable force.
So it's like the star's imploding and then exploding outwards all at once.
Pretty much.
That sounds incredibly violent.
It's one of the most powerful events in the universe. The energy released in a supernova can briefly outshine an entire galaxy.
Wow. Just imagine witnessing a supernova from Earth. It would be like a new star suddenly appearing in the sky.
It would be an incredible sight to behold, and these supernovae aren't just visually stunning, they're incredibly important for the evolution of the universe.
Okay, I'm all ears. How do supernovae play a role in the grand scheme of things?
Well, supernovae are responsible for scattering heavy elements forged in the star's core throughout space.
Okay.
These elements, like carbon, oxygen, and iron, they're the building blocks of planet's life and everything we see around us.
Wait, so you're telling me that the atoms in our bodies were once part of stars that exploded billions of years ago? We're literally made of stardust.
That's a beautiful way to put it. The calcium in your bones, the iron in your blood, all of it was created in the heart of a dying star and scattered across the cosmos by a supernova.
That's mind-blowing. So not only do supernovae create the elements for life, but they also trigger new star formation by compressing nearby gas and dust.
It's a full circle moment.
It really is. It's
Yeah.
a cycle of death and rebirth on a cosmic scale. And from the remnants of these supernovae, even more exotic objects can emerge. Neutron stars and black holes. Okay, now we're getting to the really mysterious stuff. Neutron stars and black holes, they sound like something out of science fiction.
They do have a certain mystique to them.
What exactly are they? All right, so we're back with Cosmos in a pod and ready to unravel the mysteries of neutron stars and black holes. These objects are like the ultimate cosmic enigmas, pushing the boundaries of what we thought was possible.
They really are. They're the remnants of massive stars that have reached the end of their lives, collapsed under their own gravity, and transformed into something extraordinary.
Okay, so let's start with neutron stars. You mentioned that they're incredibly dense. Can you give us a sense of just how extreme we're talking about here?
Imagine taking the entire mass of the sun, all that fiery churning plasma, and squeezing it into an object the size of a city. That's the density of a neutron star.
Wow. That's hard to even wrap my head around. What would even happen if we could somehow bring a teaspoonful of neutron star material back to Earth?
Let's just say you wouldn't want to be standing anywhere near it. A teaspoon of neutron star material would weigh billions of tons on Earth. It would probably punch right through the planet's crust.
That's insane. It's like something out of a superhero comic book.
Yeah.
But what makes neutron stars so dense? What are they made of?
They're made almost entirely of neutrons, subatomic particles that are usually found in the nucleus of an atom. When a massive star collapses, the protons and electrons in its core are forced together, forming neutrons.
It's like the atoms themselves are being crushed,
Exactly.
transforming into this ultra-dense neutron matter.
Precisely.
That's wild. But it's not just their density that makes neutron stars so fascinating, right?
Right. They also spin incredibly fast. Some rotate hundreds of times per second. And as they spin, they emit beams of radiation from their magnetic poles.
So it's like a cosmic lighthouse spinning around and sending out these beams of light.
That's a great analogy. And if those beams happen to sweep across Earth, we see them as pulses of radio waves. That's why we call them pulsars.
Pulsars, those are the objects that send out those incredibly precise signals, right?
Yes.
I've heard that astronomers use them as cosmic clocks.
Exactly. The signals from pulsars are so regular that we can use them to study a wide range of phenomena, from the nature of gravity to the structure of our galaxy.
That's pretty amazing. We're using the remnants of dead stars to unravel the secrets of the universe.
Yeah.
But let's move on to the even more mysterious objects. Black holes.
Yes.
What exactly are they?
Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They're the ultimate cosmic traps.
So anything that crosses the event horizon,
Right.
the boundary of a black hole, is gone forever.
That's the current understanding. Once you cross the event horizon, there's no coming back. The gravitational pull is so intense that it warps the fabric of space-time itself.
That's both terrifying and fascinating. But if black holes don't emit any light, how do we even know they exist?
We can't see black holes directly, but we can detect their presence through their effects on the surrounding matter.
So we look for clues like detectives at a cosmic crime scene.
Exactly. For example, if a black hole is part of a binary star system, we can observe the companion star orbiting around an invisible object.
It's like a cosmic dance with a phantom partner.
It is.
What other clues do we look for?
As matter spirals into a black hole, it gets superheated and emits X-rays, which we can detect with telescopes. This is one way we can pinpoint the location of a black hole.
So black holes might be invisible,
Right.
but they leave behind these telltale signs, like cosmic fingerprints.
Precisely. And by studying these signs, we're slowly piecing together the puzzle of black holes and their role in the universe.
It's incredible how the death of a star can lead to the creation of such extreme and fascinating objects. From neutron stars to black holes, the universe is full of surprises.
And each of these objects tells a story about the life and death of stars, reminding us that the universe is this constantly evolving and incredibly complex place.
Well, we've covered a lot of ground today, from the birth of stars and these vast nebulae to their dramatic deaths and the mind-boggling remnants they leave behind.
It's been quite a journey.
It really has. And it's a journey that continues. As we delve deeper into the cosmos, we're sure to uncover even more secrets about stars and the mysteries they hold.
I can't wait to see what we discover next.
Thanks for joining us on this cosmic adventure. Don't forget to follow and subscribe to Cosmos in a Pod for more deep dives into the mysteries of the universe. Until next time, keep looking up and keep wondering.